Hello there, and welcome to the machine learning course. In this course, we'll be studying topics regarding machine learning, different algorithms, different methodologies, and numericals. This is an exam-based point of view lecture course. So we'll be studying topics that are relevant to examinations and how you can solve different questions for examinations. So starting off with how a machine actually understands the difference between images, between different objects in an image. We are going to look at this example of elephants and dogs. We can see that elephants are larger and dogs are relatively smaller. They have different features. For this, what the machine does is how we can understand that is by plotting a graph. So in this, we take features, which is weight and height. Okay, so dogs have a shorter height and they have a lighter weight. Elephants are heavier and taller. So in this graph, we can see that the weights is on the x-axis and the height is on the y-axis. The dogs lie in a lighter and smaller weight group while the elephants lie over here. This is how a machine differentiates different objects. Since it doesn't have any understanding of images, it takes features or different variables data and accordingly it processes the data and understands them. So for now, this is unlabeled data. There is no label associated. These are just two different groups. This is just data. We don't know which one is dogs, which one is elephants, right? So once we understand the differentiation of the machine, what it does is it creates a threshold value. So this is what separates two different groups of data. So we have a group that is lighter and shorter, and we have a group that is heavier and larger. Okay. So the threshold between the two of them is this line drawn by the computer, and hence through the logic that dogs are lighter and shorter, we can classify this data as dogs and this data as elephants. So these are our labels now, and this is how the machine differentiates between elephants and dogs. So AI is the science of making machines do things that would require intelligence if done manually. AI basically refers to understanding and performing tasks that mimic human intelligence. There are three different fields. AI is the general field, artificial intelligence, where any technique which enables computers to mimic human behavior. So this talks about any technique or algorithm or code or model that mimics human behavior. Machine learning is a subset of AI, and these techniques use statistical methods to enable machines to improve with experiences. So here it just mimics the human behavior. Here it is an improved version with statistical methods such as probabilities and mean and all those things. Lastly, we have deep learning, which is a subset of machine learning, which makes the computation of multi-layer neural networks feasible. So this is a much more advanced method of AI, which is based on machine learning. Now, understanding the difference between traditional learning and machine learning. Traditional learning is simply our program that we learned through programming languages and what we've been doing in the past. It has data, which is inputs and whatever variables or constraints you provide it. And we have a script or a program that is passed on to the processing unit. Lastly, we get an output from this schema, from this flow. On the other hand, what machine learning does is we have a two-step process. So first we have a step where there is training data. So this is data that we have that is used to train a model. Fine. And we have an expected output. So this is input, and then we also give it an output through which our processing unit can train a model, which understands that on the basis of this input, we are supposed to get this output. Fine. On that, we get a trained model. Now, this trained model is used with test data. So what happens is now we have new data. In this step, we do not give the expected output. In this step, we just have a model with data, and on the basis of processing, we get an output. So this is machine learning, a two-step process where first you train the model, and in the second step, you test it out. The formal definition of machine learning is a computer program is set to learn from experience E with respect to some task T and performance measure P. So a computer learns, which is its experience E, and it is based on T and P, which is the specific task and the performance that we measure out of it. If its performance at task T as measured by P improves with experience E. So basically task is what needs to be done. such as does it have to predict or does it have to classify. The experience is the data that we provide. This is called as experience, and the performance is the measures of different things such as accuracy and precision and so on. An example is score prediction. We have students that are studying, so we have data. Fine. The experience or the data is as follows. We have multiple different students, the number of lectures they have attended, and on the basis of this attendance, we have score in chemistry that they have. We use this data to train the model. We give this as input, both of them, X and Y data. And on the basis of that, we have a trained model. Now, our task is to predict the score in chemistry. So we give some new value of X. X is our lectures attended. And on the basis of that, our model will then predict what score they're going to get in chemistry. Then this is the task where input is the number of lectures attended and the output will be the score. So on the basis of that, we can measure the performance where the y is the actual value, okay, and the y dash is the predicted value. And from that, we can calculate the error from the model, and that will be our performance. Now, there's different types of machine learning. So we have supervised learning, we have unsupervised learning, and we have reinforcement learning. These three sub-branches are part of machine learning. Starting with supervised, this is task driven and it predicts future values. Supervised, as it states, we supervise, we oversee the process of teaching. In this one, we provide labels to the machine, and these labels are given so that it knows what is the input and what is the supposed output, and accordingly it learns. An examples of these are classification and regression models. Classification is where it categorizes them into different labels, and regression is where it actually gives you a value. So a range of values can be taken. It's not just binary or class label wise. Example of classification is sorting as spam and not spam, while regression is predicting the score. So your score could be anything from 0 to 100. So this is what regression is. Examples of regression is not just score, you can also have the temperature in on a particular day, you can have the prices of a house and so on. Unsupervised learning is where data is given but you don't actually have any labels. So what the machine does is it trial and on the basis of trial and error, it classifies it into different clusters on different features. So for example, this is classification on the basis of number of legs. So 4 legs classified in one place and 2 legs classified in the other. Similarly, unsupervised does not have any labels, while supervised provides certain labels. Lastly, we have reinforcement learning, which learns from the mistakes. So we have a model that learns from its mistakes. For example, this is the model. It performs an action, you give it a reward, fine. And from that reward, it has certain observations, it keeps certain observations, and from those, it keeps improving. This model is the third type of machine learning model, and hence it learns. Similar to a maze. So you have a model that is in an environment, it performs a certain action and it reaches a dead end. So you would give it a negative reward. So it would go to a different path. And when it goes to a different path, it sees that you can move forward. There is no dead end. So you give it a positive reward. Similarly, it keeps learning. Here we have a comparison of supervised learning with unsupervised learning. So in supervised learning, we have training data is labeled, as I said. We label the data, and on the basis of that, we can train the model. It is task driven, so it's based on a task, a certain task, as in what we want the model to actually perform and do. Two types are classification and regression. In this example, we have apples and bananas. Okay, we've given images of apples and of bananas to the model. Okay, and we've labeled them. There's different types of apples, there's different types of bananas. We send it to the model for training. We train the model, and on the basis of that, we get a trained model, a final model, and then we give it some testing data. Fine. So when this data goes to the model, it can successfully predict that it is an apple. This is our prediction category. See, in this one, we are giving labels, and on the basis of a task where it is for identification, which it's for classification, we are getting an output. In unsupervised learning, we do not have any labels. This is data driven because you are using data to understand different trends, and examples are clustering and dimensional reduction. For example, for the clustering example, we can see we have 9 different inputs. Okay, we do not have any labels. So the machine does not know what each image represents. These are just images for the model. Fine. We give them to the model, and on the basis of certain features which the model identifies on its own, it clusters them. Now, in this case, it clustered them on the basis of color. So you have different colors. On the basis of that, you have 3 different clusters that the model made on its own. Okay, so this is the difference between supervised learning and unsupervised learning. Example between classification and regression, right? These are supervised learning. What is the difference between the two? First of all, classification has discrete output while regression has continuous. So discrete means it will give you either a certain class, okay, it will basically separate or sort the outputs into a defined number of different types or classes. On the other hand, regression can give you anything from a certain value to a certain value or anything in between. Okay. Classification tries to find a boundary, while regression tries to find a best fit line where the outcomes lie either, on the line, closest to the line. Most outcomes should lie, as we studied in different in the past, that points should lie closest to the line. This is what regression does. Evaluation is based on accuracy and based on sum of squared errors. These are 2 different things you can remember. These 2 methods for evaluating each of the types of models. An example of classification will it be cold or hot tomorrow, right? So what classification will do is based on the data, based on the training that it's been given. It will either tell you if it's going to be cold or it's going to tell you if it's going to be hot. On the other hand, what regression is going to do is it's going to give you an actual temperature prediction, that what will be the temperature tomorrow. Will it be 42 degrees, 45 degrees, 35 degrees, 37 degrees? It's going to give you a range, a value in a range on which it's been trained. So you will give it a history of temperatures, and on the basis of that, it will be trained, and then it's going to predict what the temperature is going to be. Now, there is obviously a process of how the machine actually learns. Okay? So, how machine learning works. So, this is the process where we start with defining objectives. So, obviously, we need to know an objective, we need to know a certain point, as in what we need the model to do, right? So, for example, in this example, we'll take classifying emails as spam or not spam. Then once we define the objective, we collect data. Fine. We are going to collect samples of spam emails and sample of important or not spam emails. After that, we're going to prepare the data. So you have to separate spam and you have to separate not spam. Okay, you have to, you know, work with the data. You have to classify, you have to clean and pre-process the data to make it good enough for the model to work with. After that, you're going to select an algorithm. You're going to select a model, as in which model do you need? Do you need a classification model in this case, or do you want a regression model? Do you want dimensionality? On the basis of that, you're going to select your specific algorithm. In this case, we need to, sort between spam or not spam, which is a classification model. So here we're going to select a classification model. The next step would be to train that model. So we'll take this data that we've prepared and we'll take this algorithm and we'll put them together to train a model. Lastly, we'll test the model to see how well it works. Okay, so we'll give it some sample data, some emails, and we'll see how well it classifies them. We know what classification they are out of these 3, which one is spam, which one is not spam, but we won't tell that to the model. Okay, and we'll just give it to the model and we'll see how it classifies them and how accurate it is based on the probability. Lastly, if the model is good enough, we are going to integrate it into our workflow and we're going to use it for, daily use. If it's not good, then we'll go back to the training model step and we'll train it again with the different data or different, factors that will change. How do you collect data for the first step? So there's different types of data. There's images, there are facial recognition videos, you can have activity, you have sensor data, you have speech data, you have biometric data. You also have demographics, you have tabular form, you have graphic form. There are so many different forms of collecting data. So based on what the data is, you will accordingly pre-process it and accordingly choose your model. There are different steps in data cleaning. First of all, we have unwanted observations such as duplicate observations or repeated observations, irrelevant values that are outliers. So you'll remove these. You have missing data where some values are not there or they are incomplete entries in the data. Then we have noisy data such as mislabeled data, or we have to fix problems such as same attributes with different names. Noise is basically unimportant or bad data. You have a big data set and then you have some images or some values that do not match or cause issues where the model would not train well. Then we have inconsistent data, unwanted values that do not fit the data set or outliers. For example, you have a data set on the weather. Okay, you have different temperatures, and then most of the temperatures lie between 37 to 45, and then suddenly one of them is 100 degrees. So that is inconsistent data. You remove that data or you deal with it accordingly. An example to see how you treat data is, first of all, the solution for cleaning data is ignoring or filling manually or using ML and mathematical tools to either fill them or replace them or drop them. So we have uniqueness. So ID cannot be same. So this is some error in data format. All the birthdays are in this format while this one has a different format. This has year first, right? Similarly, we have attribute dependencies. Okay. So is teacher and students. Okay. So accordingly, there is difference. Okay. In the data. We have misspellings. There is no such country as, so it's Italy, but they've spelled it wrong. So you fill this manually. You have misfielded values. Okay, so instead of city you have a country over here. So either you remove this entry or you have to fill it manually. Invalid values, gender is either M or F, you can't have A. And lastly, missing values. So all these values have to be treated and fixed so that the data is, it makes sense to the machine rather than becoming all absurd. How do you give data to the model? You can't directly just pass the data to the model. You need some, preparation for the data. So first of all, data is collection of examples, observations, instances, and samples. And then data has features. So features are a descriptor of the object. Okay. So this is what describes the object. You have data on that, and this data has multiple different features that are describing the object. Feature is derived from the data and it represents the data. It's the properties, attributes, parameters, or so on that describe the data and what the data actually means, its meaning. So when you get a data, you're supposed to select features from it that the model needs. Okay. You won't give the complete data to the model, otherwise the training will be inaccurate. You will select certain features that have the maximum impact on the output, and accordingly you will then train the model on the basis of those features. Now, how do you represent features? First of all, what are features? Features can be anything in, for example, taking your face. You have the distance between eyes, you have width of the nose, you have depth of the eye sockets, and shape of the cheekbones, length of the jawline, and all such features. This is what features is. That's how you define someone's face. The color, the shape, the size, the difference, and the spacing, and so on. These features can be represented in the form of a feature vector. Okay, for example, person I. Okay, so this person I, for that he has five different features. So you'll have x1, x2, x3 for x5 till x5 for this person for this specific example. In general, you can say xi as in person I has xi1, xi2, and xim features. Okay, so 1 into m feature vector for ith observation. M is the dimensionality. Okay, so number of features for a specific object. You can make a feature matrix out of it where you have for the first number of features for the first object, then second object, and so on. And n would be the size of data, number of objects or number of observations. Lastly, we have another vector y, which tells you the target label. For example, person one, if his name is John, so the first feature vector is for John, and for Jane, and so on. So this will be placed here, and you can see John has the following features, Jane has the following features, and so on. Now, feature representation in terms of feature space. Each observation is a point in M dimensional feature space. Now, you can understand this with the help of graphs of what feature space actually is. So, the case, we have three different cases, okay? Ideal case, realistic case, and poor case. Perfect discrimination is where you have Jane, you have John, and you have probably another person, okay? There is feature 1 and feature 2, okay? For example, the distance between their eyes, okay? So Jane has these following the features of Jane are as follows यहाँ पे, like they're put into this point of the graph. And on the other hand, for John, they are spread in the following manner. So you can see it is perfectly, spaced out. There is no mixing between Jane and John's features. So the model will easily be able to learn and, understand these features. But this is ideal. This is not realistic. Obviously, there is going to be some overlapping in the data. Okay, you cannot have such perfectly spaced data. So the realistic case is where there is good discrimination. See, there is some overlapping between Jane and John, but there is a difference still. You can see John is grouped here. More the majority of the the mean will be lying over here in this part, while Jane is lying over here. The case of poor discrimination is where they are completely mixed in and you don't really have a mean separation. You cannot cluster it well, you cannot create good groups. So these are three cases. Majorly, you have the realistic case and the poor case. This is just the ideal case which you would really want which you would want to achieve, but you will usually end up with this case. Now, feature scaling. What is feature scaling? Feature scaling is when, different attributes may have different ranges, hence normalization is required. What does this mean? Like, you have multiple different attributes or features of an object, right? If you're comparing multiple different objects, each of the objects can have a different range, but you want to compare them, right? You want to put them together. So what you're going to do is you're going to scale them and you're going to bring them onto the same level. You're going to try to bring them onto the same value. So there's two different methods of normalization. The first one is standardization or z-score. In this, you rescale the data so that the mean of the data is 0 and the deviation from the mean is 1. So this is in the form of the bell curve. If you remember, we had the bell curve where the center was the mean. Okay, so we will try to relocate the mean towards 0 and we'll have deviation from -1 to 1. The formula for that is x norm equals x minus mu over sigma. So mu is mean and the sigma is the standard deviation from the mean. The second is min-max normalization, where you scale the data to a fixed range. This range is from 0 to 1. For this, again, our formula x norm equals x minus x min over x max minus x min. Okay, so this is what helps you scale each feature of an object. For example, like you can understand the difference between an elephant and a mouse. Okay, you want to train a model on the basis of this, right? But the elephant is exceptionally larger than the mouse, okay? And this will cause issues in training the model. There might be confusion and changes. So what you're going to do is you're going to scale them. You're going to make the mouse bigger and you're going to make the elephant smaller until they reach a certain balance where they both are of a similar size. And then you can compare their ears, their nose, their trunk, the tail, and so on. This will efficiently help you understand the model. So an example of feature scaling is standardization. First of all, we're taking the example of standardization. Okay. In this, we have this table, which is to predict house pricing. So we have the square feet, the number of beds, the number of baths, and the size in acres, and the price accordingly. Okay. Now you can see in terms of square feet and beds. Okay. Um, the numbers, the values, the ranges are huge. So this is in thousands and this is in, ones. 2 beds, 6 beds, 4 beds, but this is 1300, 2700, and so on. So what we're going to do is we're going to normalize these two values to bring them into the same range. Once you go for square feet and you normalize this by putting it into the equation, you find the mean, you find standard deviation, and for per value, you then put them into the equation and you find the standardized square feet. You can see it lies from minus 1 to 1. The range mean is closer to 1 and the mean lies in 0. So accordingly, you standardize this into a range of something from -1 to 1. that sort of range. Similarly, for beds, you did the same thing. Again, it is some values are 0, some values are minus 0.53, some are 1, some are minus 2. So minus 1.2. So you can see the difference. Before we had thousands and twos, now we have minus 1 point something, minus 1. They're very close now. It's standardized. You have a fixed scale where you're measuring things. The same thing can be done using min-max normalization. Now, what happens in min-max is instead of the negative values, you have everything from 0 to 1. It lies from 0 till 1. So you standardize them. Here is square feet 0, 1, 0 0.5, 0 0.3, 0 0.4. Similarly for beds 0, 1, 0 0.5, 0 0.25, 0 0.5. So these are normalized values for square feet and beds relatively. Why didn't we take the other things? Because see, baths is similar to beds, right? 1, 2, 5, 4. And acres is also 0.2 till 5.8. So these values they don't have such a big jump. But these two values had a very big difference. So we normalized them. So this is why feature scaling is important. Now, when to use z-score normalization and when to use min-max. We need to understand this so that you can utilize the best approach at the best time. So if you're using a machine learning algorithm which is sensitive to scale of the features, right? You're using an algorithm which has, the output will drastically change if you change the scale. Then z-score is important. It is a good option. Or if you are considered regarding the noise in the data, so you have you have lots of noise, you have lots of irrelevant data, but you do not have the time to change that, and you just need to apply the algorithm, then you are going to use z-score again in the same case. Now, if you have an algorithm that is sensitive to the range, right? A slight change in the range will cause change in the output. So in this case, you are going to use min-max. And similarly, about distorting if you're concerned about the distorting of the distribution of the features. So you do not want to distort the features, okay, their distribution, then again, min-max is the best option. So this can come in the theory part. You can just write these 4 points and they should be enough. Now we are going to understand feature engineering with the example of classification of animals. So we have these examples over here: the viper, the cobra, emerald tree boas, rohu, a fish, crocodile, golden poison frog, and python. Okay, so we're going to use all of these animals and we're going to classify them into reptiles or not. Okay, so this will be our table. These are the features. So we've got the names of the animals, we've got the true and false value of whether they lay eggs or not, whether they have scales, are they poisonous, are they cold-blooded, number of legs, and reptile or not. Fine, this is the label. Now, how do you choose the label? Clearly, the label is going to be the one which tells you what, the goal is. What is the objective? What is the objective? To classify whether these animals are a reptile or not. So this will be our label. What are the features? Features are all of these. This one, two, three, four, five. Five of these are the features, and this is the name. Now we're going to choose specific features that are going to give us the best outcome, and we'll see that in the next slide. So initially, we have the following features: egg laying, scales, poisonous, cold-blooded, number of legs, and reptile is our label. Fine. Number of legs in the following two cases are 0 for each. Okay. We have two cases right now: the viper and the cobra. Okay. Then we are going to add a different, we are going to add another case. Now we've added emerald tree boas. Okay. Now look at the following. They lay eggs, false, right? In this one, scales is true, poisonous, false. There's a difference, right? But all three of them are reptiles, right? So we need to choose features that, that show that these three features are representing reptiles. So now we are gonna remove the poisonous and the egg laying feature because there's a difference in the two. But the number of legs, whether they're cold-blooded and scales are the same, right? So we've removed any useless cases such as false, which will cause error in the reading if we include all of them, right? So there is a difference in two values. Hence, there is a chance the model will predict emerald tree boas as false, as it is not a reptile. Hence, we remove those two features and we add the remaining three: scales, cold-blooded, and no legs. Going for the third animal. In this case, we added a crocodile, right? So now, till now we had legs 0, but now we have a range from 0 to 4. Okay, so the reptiles can either have 0 legs or 4 legs. Adding the last two options, the golden poison frog and the rohu fish. Okay, so now in this case, these two are not uh, reptiles, right? But in this case, you can see rohu fish has the same readings as that of the reptiles. It has scales, it is cold-blooded, it's got 0 legs, but it is not a reptile. The model will misclassify that, right? And then adding Python as well. So features of Rohu and Python are exactly the same, but the difference is their label is different. One is not a reptile and the other one is a reptile. Okay. So the best features that we can choose is cold-blooded and scales. Fine. Scales and cold-blooded. Now what happens in this case is we are not considering the number of legs. Okay. So the model will not be perfect. Okay. You cannot choose a specific set of features which will give you a perfect model. One or the other will give you, errors. So this model where we choose scales and cold-blooded or not has the following disadvantage. No false negative, okay? So anything classified as not reptile is correctly labeled, okay? So not reptile, what is it? No, this is the case and this is the case, right? Anything that is not reptile is correct, which means cold-blooded false and scales false, okay? So whenever you give these false, it will always tell you that yes, this is not a reptile. This will be true. But there are some false positives. Some animals that are not reptiles could be classified as reptiles. Now this is the confusing part, but try to understand. No false negatives, okay? So if you give data to a model, if you give the data of golden poison frog, right? It does not have scales and it is not cold-blooded, then the model will always classify that as not a reptile. Okay? It will not give you any false negative. None of the reptiles will be classified as not reptile. Get it? That is what this means. So if you give viper or cobra or emerald or crocodile or python, none of them will be called as negative. Okay? But some false positives may be there, okay, which is in this case the rohu, the fish. This can be a false positive. Now we need to understand what false negative and false positives are. We'll study that further on. um, this rohu fish will be classified as a reptile. This is a false positive. That means a false positive, as the name states. A positive which is not correct, it is false. You cannot, that is not a reptile, yet the model says it is a reptile. But there won't be any false negatives where it says it is not, but it actually was a reptile. Okay? False negative means that it is not a reptile. False negative means that the model says it is not a reptile, but it actually was. The model is wrong. So we won't have any of those because all the reptiles have the same values in terms of cold-blooded and scales. See, viper, cobra, emerald, boas, crocodile, and python all are true scales, right? And similarly, all are cold-blooded. So the model will not classify them as wrong. Now there is a need to measure distance between features. Okay, till now we just took features randomly. Now we will see how feature engineering takes place. This means we decide which features to include in the model by measuring a distance. Okay, so the distance helps to it helps to measure distances between training data points and new instances. When you measure these distances, it tells you which feature has a bigger impact and which is not as important. As it says, it helps decide how weight relative importance of different dimensions in feature vector impacts the different definition of distance. So how does the model actually change based on different features? First of all, measuring distance between animals. Okay, so we can see in our case, which we studied earlier, each animal has four features, like four binary features: egg laying, scales, poisonous or not, cold-blooded or not. These were true, false, right? But only one integer feature, which is legs from 0 to 4. You can either have 0, 1, 2, 3, or 4 legs. Okay. So one way to separate them is to measure the distance between the pairs of data points and use that to cluster examples together in a common class. Or the second would be to find a classifier surface in feature space, which separates them. To find like we saw earlier, the separation, to find a graph, okay, to separate them with a line or any curve. So converting them into feature vectors. First of all, you can see each of our cases, we've converted them into a feature vector based on the features. Okay. Viper 11110, which means it lays eggs, it has scales, it is poisonous, it is cold-blooded, and it has 0 legs. Similarly, the rest of them are converted as well. Considering the first approach, we will measure distance between pairs of data points. Okay. These pairs of data points means animals per animal. Okay. This is a pair of data points, this is a pair of data points. We'll measure distance between each of them, and then we will cluster them into common classes. Okay, now how do you measure differences? We have two different formulas. Basically, it's the same formula, you just change a value and it becomes two different types. Okay, so you have distance of point 0.1, point 0.2, and value of p. If p is 1, then it is called Manhattan distance. If p is 2, it's Euclidean distance. So it is the summation of the absolute values of x1 minus x2, okay, square, like p, power p, and root of p. So either it is going to be, if it's 1, if p is 1, okay. So Manhattan distance is the sum of the absolute value difference of the 2 points, okay. If it is 2, then it is the root, okay, it is sum of the root of the squares of the two differences. We'll see them in the example. Euclidean distance represents the shortest distance between two vectors, okay. It's the square root of the sum of the squares of the differences between the corresponding elements. So it is a square root, okay, of the sum of the squares, differences between the corresponding elements, their squares, and them summed. So when you add the squares and you put a root under them, that's how it is. Manhattan distance, on the other hand, is the sum of the absolute differences between points across all dimensions. So there is no square, there is no root, okay, you just find the differences, okay, and you make an absolute value out of them and you sum them together. Now here is a graphical representation. Manhattan is the absolute difference summed, okay. So P1, a point A and B has P1 Q, P2 Q1 Q2. So P1 minus Q1, P2 minus Q2, difference, and their differences summed. That is Manhattan. Simple. On the other hand, P1 minus Q1, square that, okay. P2 minus Q2, square that, add the two, and then apply square root, okay. That is Euclidean distance. This gives you the direct distance. Manhattan gives you dimension wise, okay. So first, how far you have to travel on the y-axis, and then how far on the x-axis to reach that point. So this is the visual representation. Let's take an example to see this. We have a circle, we have a star and a plus. Okay, we need to see how you're gonna, which the Manhattan distance and the Euclidean distance for both of them, circle to star and circle to plus. Okay, typically Euclidean distance is used because Manhattan may be appropriate in dimensions that are not comparable. So in this case, you have x and y, you're just comparing two steps, right? So both the dimensions are same. If you have any dimensions that are different or not similar, then you can use Manhattan, but usually Euclidean is a better option. In this case, we have added the values. So let's see how we got each of these values. First of all, from circle to plus, okay, to the cross in terms of Euclidean distance. Okay, so our distance is from circle plus, okay, and since we're using Euclidean, we're gonna write 2 for p, okay. So it is the root, okay. The dimensions for this is 0 0, and this is 1 2 2 2 up and 2 towards the right, right? So 2 2 on the grid. So we have 2 minus 0 and 2 minus 0, okay. So 2 minus 0 squared plus 2 minus 0 squared and rooted. You can write 0 minus 2, same thing, because you're taking the absolute value over here, so it doesn't make a difference. You're going to get root 8, so 2.8, as we found. Then we're going to take it for the star, okay. Again, star is on, in terms of the x-axis, it is at 0, but on y it is 3 steps up. So circle is at 0 0 and star is at 0 3, okay. So 0 minus 0 squared plus 3 minus 0 squared, so you're going to get root 9, you're going to get 3, distance is 3. So star cross is 2.8 Euclidean distance, and star is 3 Euclidean distance. Now let's calculate Manhattan distance. Again, circle to cross, okay. Simpler, this is just 2 minus 0 plus 2 minus 0, again absolute sum, which will give you 4. Okay, see the difference? In Manhattan, you're getting 4, okay, 1 step, 2 steps, 3 steps, and 4th step. But in Euclidean, you're getting 2.8 steps. You're getting the direct distance. Okay. And for the star, okay, for the cross, you got 4. For the star, you are gonna get 0 minus 0 plus 3 minus 0, 3. So 3 steps, and that is the value. Now we are going to apply the, like we said, Euclidean is a better option most of the time. We're going to apply Euclidean distance on our previous example of animals. Okay. So our feature vector is egg-laying, scales, poisonous, cold-blooded, and legs. These were all our features, right? And we have viper, emerald boas, and frog. These are the feature vectors for each of them. We will apply Euclidean distance between them. Okay, so how do you make the table? Simple. Um, place the 3 objects, okay, animals, 1, 2, 3, 1, 2, 3, like that. And then diagonal elements are going to be 0, obviously. So viper is going to be 0, boas are going to be 0, and frog is going to be 0. Then you are going to apply the calculation. Let's calculate between viper and emerald tree boas. Okay, viper, emerald tree boa, Euclidean distance. So it is the root of the sum of the squares of the difference. Root of the sum of the squares of the difference. So 1 minus 0 squared plus 1 minus 1 squared plus 1 minus 0 squared again, okay, plus 0 minus 0 squared, and the root of that. So you're gonna get the value 1.414. 1.414, and you just need, like, you have 3 different objects, you have 3 different calculations. Obviously the opposite side of the table is going to be the same. So viper and ETB is 1.414. Similarly, ETB with viper is also going to be 1.414, sorry. Again, then you're going to calculate for viper with golden poisonous frog and emerald tree boas with golden poisonous frog. You're going to get these 3. Okay. From the table, you can see both snakes are close to each other. So how do you see that? Viper and boas are 1.414, right? And when you look at the frog with the viper, it's a big jump. From 1 it goes to 4. Similarly, snake with frog, big jump. Snake with frog, big jump. Snake with frog, big jump. So these are 4. But these snakes are close to each other, while the frog is distant from them. Now we're going to add a new animal. These were our 3 initial animals. We'll add crocodile now. Fine. In this one, we are going to calculate again. What happens after the calculation is, again, the calculations are intensive. Across the diagonal, the upper and the lower diagonal elements are going to be the same. Okay. What you see is the boas are same, right? 2 snakes are closer, but the crocodile is closer to the frog. Crocodile frog and crocodile frog. They're closer values, right? Frog to the snakes is fine, but crocodile to the frog is closer because of the legs. Okay, because of the legs. So now what you're gonna do is, there is an error over here. This is supposed to be 4. Here you have 4 legs. Okay, so 4 legs and 4 legs, similar number of legs, which causes similarity, a closer value in the frog and the crocodile. Crocodile differs for frog in 3 features, from boas in only 2 features, and other feature are binary. Okay, all the features are binary except for the legs, which consists 0 to 4. Fine, the value of legs is from 0 to 4, which is, not binary. Other features are binary, but, and this is a misclassification, because right now what is the basis of our label? Our label is on the basis of reptile or not, but over here it is closer to frog, which is not a reptile. Hence we are going to use binary features. So instead of the feature leg, we will, instead of putting it in a numerical value, we will change it to either it has legs or does not have legs. Fine. So now all of it becomes 0 0 1 1. When you find the values again, now crocodile will be closer to snakes than to the frog. Okay, how is that? Crocodile values with the snakes is 1.4, 1.4, 1.4. You see all the values. Snakes and crocodiles are closer, the values, while crocodile here again with snakes is closer. Okay, but crocodile with frog is not as close. So 1.7, the difference is 1.7, 1.4. Minor difference, yet there is a difference. Okay, so this helps with classification. Let's individually see the upper table. Viper with snake 1.4, okay, viper with frog 1.7, viper with crocodile 1.4. This shows that 1.4 and 1.5, these 1, 2, 3 animals can be classified into one group, and 1.7 is an outlier that will be a separate group. Similarly, you can, study each of the features and understand what the table means. Now, understanding clustering approaches. What are clustering approaches? Suppose there are k different groups. Till now, we knew the groups, right? We had snakes. We had two groups, okay, reptile and not reptile on different animals. Suppose there are k different groups in our training data, but we don't know their labels. We don't know if it is reptile and not reptile, okay? And data could have any groups, right? In our previous example, it was two. So what we're going to do is we're going to pick k samples at random from the training data, and for every example we are going to put it to the closest cluster. So we'll make k samples, and out of those samples the objects we're going to put them to the closest sample we took. Once we get these clusters, we find a median and we repeat until there is no change, which tells us that we have found different groups, okay, and we've put them into the closest group, and we have separated them in something that would be the right separation. What is the issue? First of all, how do we decide the number of clusters? How do we know that there is exactly two or three clusters in the group? And secondly, how do we select the best feature or the best distance metric to, separate them? If we do not know the label, then how are we going to select the feature that divides them into that label? An example of unlabeled data is distribution of weight versus height. Now we can see the data here, so we can tell, right? There is one different type of data, a second type, and a third type. So this needs three different clusters. Okay, but how are we going to do that when we don't have the label or when we can't see the difference? Okay, because see, the data is pretty close together. First of all, we're using two clusters. Once we use three clusters in an unsupervised manner, you have distribution. See, all these are the same type of data, mixture of data. So this is an issue in this clustering approach. The second approach tells us, which is the classification approach. We find boundaries in the feature space instead. Feature space basically refers to the graph where you point the features, you place the data in the form of a graph. So they separate different classes of labeled data. Okay, so for simple surface, that's either you look for simple surface, which is a single line or a plane. Okay, that separates, or you look for something more complex where there is a whole, different curve or sort. Then you use voting schemes. Again, issues in this is avoiding overfitting of data, or measuring the performance, or selecting the best features. Let's take an example. There is a random division of data into, training and test set so that we can understand. The triangles show Congress and the circles show BJP, and it is separation in the basis of distance from Noida to age. So these are our features, and this is the data. There are two ways where we can, separate this, either in this manner, okay, where majority of the Congress is over there and rest of the BJP is here, or we can also separate it with this line. Okay, let's study the difference between the two. So we need to understand the confusion matrices, which tells us the training error. First of all, let's understand this. This side represents the actual and this side represents the predicted. This is what the model gives you, this side, and this is what the actual labels are. Okay. So positive, negative, positive, negative. It is a matrix again, and you need to understand four different values: true positive, true negative, false positive, and false negative. True positive is where the actual was positive and the model predicted positive. Okay, so that means yes, it was a hot dog in reality, and the model also said it is a hot dog. Hot dog. True negative is where the actual is negative and the model says it's negative. So this is not a hot dog. Okay, in reality, it is not a hot dog, and the model also says that it is negative. This is not a hot dog. False positive is where the actual value is negative, but the model says it's positive. So in reality, this is not a hot dog. This is just a costume. Okay. But the model says, yes, it is a hot dog. So this is a false positive. This is a wrong, implementation. And false negative is where the actual value is positive, but the model says it's negative. Now this is a hot dog, but it is slightly different from, in the image. The image is slightly different. So the model predicted it as wrong, that no, this is not a hot dog, but it was actually positive. So these are the four cases that are there in a confusion matrix. Now applying the concept of confusion matrix on our example, first look at the solid line. Okay, so this is the solid line. So we have to see actual BJP positive. Okay, all of the BJP, the red dots, are under the line. Okay, so there are 12 dots. Okay, so that means actual positive is 12 and predicted by the model is also 12. You can see none of the dots are above the line, right? So whenever it predicts BJP, it is always gonna be positive. Okay, true positive. Okay, then you have to look at actual is BJP, but it gives a negative. Okay, model says not BJP. Okay, so what is that gonna be? That means under the line, other than BJP, we have Congress. How many? One, two, three, four, five, six. We have six Congress, right? So there is a chance that actual might be BJP, but the model says Congress instead because of the six values of Congress that we have under the line. So those are six. Then negative, okay? So actual was Congress, but it says BJP. That will be zero because above the line we do not have any BJP. Last one is it is actually BJP, but sorry, it is not BJP and the model does not predict it as BJP. These are 11 Congress above the line. So 11 will be for the solid line. So this is how the division for each of the cases in our solid line. When you look at the dashed line, again in a similar way, actual BJP and predicted BJP. Okay. Solid line, like the dashed line is here. Okay. So now you can see one of the BJP is on the right side. Okay. Hence, only 11 are gonna be predicted as BJP while they were BJP. Okay. Second case is actual is BJP, but it says that it is not BJP. This is again the Congress over there on the BJP side. So one, two, three, four, five, six of them, right? Six triangles on the left along with the BJP. So the chances of predicting these six as BJP, okay, will be here. Then we have it is not BJP, okay. So we actually had Congress, but it predicted them as BJP. That would be this one outlying point, hence one value. Lastly, not BJP, okay, in reality, and it predicts it as not BJP. Those would be these points on these triangles on this side of the line. Okay, so these 11 triangles on the right side of the dash line. This is how we can make the confusion matrix for each of them, and then we can calculate the accuracy using these values. So for solid line, true positive plus true negative upon the summation of all four. Okay, true positive plus true negative and summation of all, which will give you accuracy of 0.85 or 85%. And for dashed line, true positive plus true negative upon summation of all will give you 88%. So the dashed line is a better model compared to the solid line. A more complex model would be as follows, where you have, you know, sorted them in a very characterized manner where you are separating them as follows. This point has been put into the Congress part and the rest all BJP are together. So in this one again, true positive, false positive, true negative and false negative we have calculated and our accuracy comes out to be 92%. This is a more complex characteristic model. Hence this is better than the linear models that we had earlier. Other measures that you can have is precision, where it is true positive upon true positive plus false positive. Okay, so our precision for the model is 48, for the solid one is 48%, for the dashed line is 67%, and the complex model is 61%. Other parameters are recall, specificity, and F1 score. You can remember all these formulas and you can find them when a numerical question asks for. Now we need to understand the advantages and limitations of machine learning. This will be the last part of this module. The advantages are that you can identify trends and patterns. Okay, you do not need human intervention for making out certain, you know, for certain to reach a certain conclusion or to classify certain things. You do not need human intervention. It has continuous improvement. You can keep on training the model based on data. It handles multiple dimensional values, okay, and datas. And it has a wide range of applications such as medical and IoT in different economics and every other sort of field. The limitations are with data acquisition. You have to spend time and resources. Interpretation is hard. Okay, you will calculate different scores, and not everyone can interpret these results. Lastly, there is high chance of error if there is any issue in the data. So that's it for this module. We have studied different types of algorithms, different fields in machine learning. We have seen how feature scaling works, how we engineer different features, and how we calculate different values, what a confusion matrix is, and so on. In the next module, we'll be looking at further topics. Thank you, and see you in the next video.